Hi everyone, welcome to this new episode of FEA Insight. Today we are going to cover an FEA Academy workshop, model a highly nonlinear problem. So here is the agenda for this presentation. First, I'm going to start with a reminder about nonlinear analysis by FEA. And after that, we're going to jump into the workshop, modeling metal forming. It is this highly nonlinear problem that I want to present you. So let's start with a reminder about nonlinear analysis by FEA. In structural analysis, a nonlinear effect can occur because of three types of nonlinearity: geometric nonlinearity, material nonlinearity, and boundary nonlinearity, here in this case contact. The geometric nonlinearity occur if a continuous body undergoes large deformations. The strain displacement relations become nonlinear. Moreover, under large deformations, the stiffness of the system will change with deformation, making the problem nonlinear. Another form of nonlinearity in the geometric field relates to stress stiffening, named also tension bending coupling. The bending stiffness of an element increases because of the tension transferred in the membrane. For example, to illustrate this effect, consider a plate subjected to pressure. An increase in the out-of-plane deflection of the plate increases the membrane stresses, which significantly affect the bending stiffness of the plate. This effect can only be captured using a nonlinear analysis. Material nonlinearity, the other type of nonlinearity, if a material does not follow the Hooke's law, the nonlinear material models must be used. And finally, boundary nonlinearity. The most frequent boundary nonlinearities are encountered in contact problems. In this form of nonlinearity, the boundary conditions change with the deformation. In fact, the size of the contact surface and the contact load depend on the deformation and the load. So the stiffness metrics and the applied loading are functions of the displacements. Nonlinear problems are complex to solve by FEA. But by using the proper modeling techniques and doing the right assumptions, we are able to produce very accurate and reliable nonlinear analysis. In a nonlinear solution, compared to a linear solution, the problem is different because the famous static equilibrium equation is the one you see here on the screen. Okay, the force equals stiffness time displacement. Force is a function of the displacement, and the stiffness is a function of the displacement. And for sure, the displacement, it is the unknown. It is what you are looking for, what you want to compute. So you understand the nature here of the nonlinearity. Okay, the structural stiffness metrics and possibly the load vector become functions of the displacement vector. So it is not possible to solve for the displacement vector immediately, directly I should say, because the stiffness metrics and the load vector are not known in advance. Okay, so the classic decomposition method, the LDL decomposition method that we are using to solve a linear problem is not applicable to solve the problem directly. So an iterative and incremental process is needed to obtain the displacement vector and the associated stiffness metrics and load vector, satisfying the equations of equilibrium. At this stage, it is important to understand that unlike linear problems, which always have a single solution, nonlinear problems do not. As you will see later, even when a solution is found by a nonlinear algorithm, it may not be the solution that you are looking for. So to solve nonlinear problems, the Newton-Raphson method is used. And the Newton-Raphson method is an iterative process. Okay, for a nonlinear problem, instead of linear algebraic, instead of a linear algebraic equation, force equal stiffness time displacement, we must solve a set of nonlinear algebraic equations. Okay, this equation is the sum of internal nodal forces depending on the displacement equal the sum of externally applied loads. So it is what you see here on this graph, the graph on the left here, where the horizontal axis represents the displacement and the vertical axis represents the applied load. Here, this blue curve is your load path, your history load, sorry. And here, this point, it is the solution you are looking for. So the basic operations that the nonlinear solution is going to use are gradual loading. The load is not applied at 100%. Okay, you apply the loads gradually. The second basic operation, it is iterations with convergence test for equilibrium. And the third basic operation, it is the stiffness matrix update, because during the incremental process, the stiffness of the system will evolve with the displacement. So the iterative process is based on Newton's methods for the nonlinear static problems. And the arc-length methods also is used for nonlinear buckling problems. I'm not going to cover that in detail in this lecture, this presentation, but you can find all the details about Newton methods and arc-length methods into the online course, the FEA Academy online course, especially the practical nonlinear finite element analysis course. Okay. Also, the stiffness matrix updates are performed occasionally, okay, to improve the computational efficiency, and they may be overridden by the user's discretion. By that, I mean that you can ask the solver to decide when the stiffness matrix is updated, okay, depending on the variation of the stiffness during the iterative and incremental process. Or as a user, you can force the update of the stiffness matrix. Again, those strategies of nonlinear analysis are covered into the FEA Academy practical nonlinear analysis course. So the strategy for a nonlinear solution is based on several factors that will influence convergence in terms of computing time and solution accuracy. The loading sequence and load increments will strongly influence the solution. So to summarize the combination of the Newton-Raphson method with the incremental force methods, here I propose you this graphic. The loading is applied gradually in increments. So you see here we have a certain percentage of the load, another percentage of the load, and another percentage of the load. Okay. So you don't start, if the solution is here, you don't start with 100% of the load. You start with, let's say, 10%, after 20%, after 30%, and you progress like that. So the loading is applied gradually in increments, and equilibrium iterations at each load increment are performed to drive the incremental solution to equilibrium and satisfy the global equilibrium equation of the nonlinear system. It is illustrated here. You see here you have the iterations inside these load increments. After that you have those iterations inside this load increment, and so on until you reach the convergence for 100% of the load. So the incremental process continues until the residual parameters are within a tolerance defined by the FEA analyst. Note that the load increments do not have to be uniform, and the critical parts typically require a smaller increment size. The tangential stiffness matrix is calculated at the beginning of each load increment and is unchanged for each iteration in the load increment, unless a potential divergence is detected. So if a divergence is detected by the solver, the tangent stiffness matrix update can be forced, okay? And in order to continue the iterative process. So now let's jump into the workshop of this presentation, and let me presenting you the sheet metal forming problem, because it is a highly nonlinear problem in the sense that the three types of nonlinearity are present here. The nonlinear geometry due to large displacement, nonlinear material due to plastic behavior, and nonlinear boundary conditions due to contacts. So here are the different steps that we are going to explore during this workshop in order to understand how to define the nonlinear solution. So first it is the creation of the geometry, the creation of the FEM, and then defining the material properties, the boundary conditions, the contact conditions, and how to apply the loading, and finally the setup of the nonlinear parameters. So let's start with the geometry here. The simulation is based on a benchmark problem presented by Alcoa Technical Center in Pennsylvania, and the results have been presented in the NUMISHIT 2002 conference in Korea. This simulation involves the punch forming of an aluminum sheet in a die. So what I did the simulation using the Nastran solver, and I compared with the experimental results presented by the Alcoa team. Okay. As I said, I did the simulation with the Nastran solver, but you can replicate this exact simulation with any FEA package. Okay. All the modeling technique, the process the workflow I'm going to present you can be replicated with any FEA software, and they are valid with any FEA software. The software is not important. What is important are the modeling techniques used to set the nonlinear finite element analysis. So you see here the geometry on the slide. You have a punch, a die, and the plate that you want to form. Okay. It is really the definition, the geometrical definition of the benchmark problem presented by the Alcoa Technical Center with the result presented into the NUMISHIT 2002 conference. So the images here are showing the punch, the die, and you see, but here it's difficult to see the plate, but here you see during the forming process, you see the plate into the die, I should say, between the punch and the die. Okay, here it is the punch at the initial position and the punch at the final position. So you see here are the different geometrical parameters for the punch radius, the initial sheet length, the sheet width, the sheet thickness, the die radius and shoulder and width, and the punch stroke. So all those geometrical parameters are very important because they permitted me to define the different surfaces you see here on the left. Okay, so if you want to replicate this model, this simulation, sorry, you have to represent exactly the geometry of your model using those parameters. If you want, I already have the geometry for this model, this problem. So if you want, I can share with you. Just send me an email and I will be able to share with you the geometrical file. So now let's see the definition of the finite element model for this simulation. The FEM is made of 2D shell quad elements with linear integration for the plate. The mesh size is 0.5 millimeter. So it means with those dimensions, I obtain more than 14,000 elements in the model with 60 elements across the width and 240 elements along the length. Here I am talking about the mesh of the blue plate here in the model. So you see it's very refined, but I need that to capture the metal forming problem. Also, the fine mesh of the plate is due to the fact that we need to model a very local contact between the plate and the curved shoulders of the die, okay, here in this region. You see the shoulder of the die? So it's a very small region where you need to capture a contact. This contact is almost aligned with a large amount of sliding. Okay, so a lot of elements are required in order to capture this local effect. The thickness of the associated property for the plate, the quad elements here, is 1 millimeter. The punch and the die are not meshed, okay? They are defined as rigid bodies. So the geometry here of the die and the punch are just surfaces. I don't need to mesh them. Now let's talk about the material model. The material model, first, what is the material of the plate? The material of the plate is aluminum, the aluminum 6111-T4. Okay, the elastic properties of this material are the Young modulus 70,500 MPa, 0.33 for the Poisson ratio, and 184 MPa for the proportional limit. In that case, the model used for the nonlinear portion of the material, the plastic behavior of the material, it is the Holloman hardening model, okay? To represent the plastic stress strain data. You probably already know this model. The model, the Holloman hardening model, is governed by this equation, okay? And you see the two parameters here, the strength coefficient K and the strain hardening coefficient. For aluminum 6111-T4, the strength coefficient K is 550 MPa and the strain hardening coefficient N is 0.223. Here you have different values for different materials, okay? If you want to use this Holloman hardening model. This is from the literature. Those parameters are empirical. They are based on tests. Also, on the definition of the material model, something very important, it is the fact that we use a large strain formulation using additive plasticity. And it is very important in the case of a metal forming simulation. because large strain formulation using additive plasticity is a method used to model the behavior of materials under large deformation. It is based on the idea that the deformation of a material can be divided into elastic and plastic components, with the plastic component being represented by a set of internal variables. These internal variables are used to describe the history of plastic deformation in the material and are updated during the simulation using a set of constitutive equations. Additive plasticity is a specific type of large strain formulation in which the plastic deformation is represented by a sum of contributions from different mechanisms such as isotropic and kinematic hardening. This approach is particularly useful for simulating the behavior of material in metal forming. About the isotropic and kinematic hardening, I'm not going to explain that in detail in this presentation, in this workshop, but keep in mind that it is described in detail, presented in details in the FEA Academy Nonlinear course, which is available on the FEA Academy website. Now let's discuss the boundary conditions. First, the position of the rigid body that I call the die is controlled by removing all degrees of freedom on the body. The displacement of the punch is controlled by removing the degrees of freedom in the horizontal direction and specifying its displacement in vertical directions as an enforced displacement. Note that the y direction is the direction in which the punch is moved into the die, this axis, okay? So the plate, first I have also to specify something very important about the die, okay? The die is fixed along the 6 degrees of freedom. So the 3 translations and the 3 rotations. So the red part, which is a surface, is completely fixed, because in the reality it is the case, okay? The die cannot move in any degree of freedom, while the punch is controlled along the y direction. So it means the yellow part can move in the y direction, this axis, but is fixed along the y and the z direction. The plate now, it is the same. We have to control the degrees of freedom of the plate. When I mesh the plate, I make sure that there is a node exactly in the middle of the plate. This node is located at the exact location of half the width and half the length, okay? What I am doing with this node in terms of boundary condition, it is that I fix the degrees of freedom in the translation X, translation Z, and the 3 rotations. But it is free in the Y direction, and only this specific node. You can consider this node as in the symmetry axis of the plate. Finally, to restrict the rigid body motion, because when you define boundary condition, it is the key, okay? Restrict the rigid body motions. So to restrict the rigid body motions and stabilize the model during the spring back, and I will present the loading history next slide. Grounded 1D spring with very small stiffness along the degree of freedom Ty are added at 2 nodes located at the free ends. So again, at the middle of this edge and at the middle of this edge, I have small 1D spring, which are grounded with very small stiffness. Okay, so the objective is ready to stabilize the model during the spring back. The loading now. The loading consists of a vertical enforced displacement applied to the punch rigid body. Since the solution is nonlinear, the cumulative effect is taken into account, and the starting state of a subcase corresponds to the state of the last converged iteration from the previous subcase. So the three following subcases are applied in sequence on the punch body. The first one, okay, it is the punch in. We apply, it is the application, I should say, of the imposed downward displacement in the vertical direction to simulate the sheet forming. The enforced displacement here is 28.5 millimeter, and it is related to the dimension of the problem. Okay. Then the second subcase, it is the punch. I call that the punch maintain. This subcase ensures that the model reaches a good equilibrium condition before starting the subcase 3, which is the punch out. It is the application of the imposed upward displacement in the vertical direction, okay, to capture the sheet spring back. It is really obvious, but it's very important to present the sequence and to keep in mind that here there is a cumulative effect during the process. So now let's discuss about the definition of the contact between the three parts of this problem. I mean the punch, the plate, and the die. First, we have to discuss about the nature of the contact. Here, it is a touching frictional contact. It means that bodies can separate and can slide with resistance. Here, I want to discuss a little bit about the type of contact. Typically, with any FEA package, you have two types of contact. You have the glue contact and the touching contact. The glue contact or specific contact where you have bonded or weld contact and rough contact. Here, it is not the nature of our problem. In our problem, the contact are not glued contact. They are touching contact because you can have separation and you can have also friction. It is the last type of contact here you have on the plate. So it is a touching contact with friction. So it means in the normal direction, the contact pair can separate, and in the tangential direction, the contact pair can slide. And there is resistance between the contact bodies. Okay? It means that the friction of the problem is taken into account with a frictional a coefficient of friction. Sorry. The contact pair can slide and separate, and the coefficient of friction affects the tangential friction. Also, in the normal direction, the touching body, which is the slave body, cannot penetrate the touch body, the master body, but they can separate. So the following bodies are defined here in this problem in order to set the contact pairs. First, we define a deformable body. The deformable body are all the 2D shell elements of the plate. The blue plate here are defined as a deformable body, where the stiffness of the shell are taken into account. Then we define two rigid bodies. The first rigid body, it is the surface of the punch. Keep in mind that this one is not meshed. Okay, it is just a surface. It is the first rigid body. The second rigid body, it is the surface of the die. Again, not meshed, only a surface. Now that the bodies are defined, we need to tell the solver which bodies may come into contact with each other. And we do that by defining the body pair. So two body pairs are defined. The first one, it is a body pair between the punch, the rigid body one, and the plate, the deformable body. The second one, it is a body pair between the plate, the deformable body, and the die, the rigid body 2. Okay? And as I said before, we need to set a friction factor. A friction factor is defined for all the contact with a bilinear Coulomb friction model. This friction factor is a typical value obtained by test for lubricated metal-to-metal contact for a sliding condition between surfaces. Again, this factor comes from literature, and it is a typical factor. You can adjust this factor depending on your own problem, depending the material of your problem, and depending on is it a lubricated or not lubricated problem. Okay, this is published in literature usually. Now let's discuss about the setup of the nonlinear parameters. Here I'm just going to present you the parameters, but I'm not going to discuss in detail the influence of each parameters. Okay, again, it is covered in the course, the FEA Academy course about nonlinear finite element analysis. So here, the method. Here we're going to use the full Newton Raphson method, okay, with an update of the stiffness metrics at every iteration and on convergence for sure. The geometric nonlinear methods are large displacement effect, okay, with update element coordinates. The material nonlinear model is activated by the definition of an elastic plastic material model. As I said before, we selected the Holloman model. The nonlinear boundary is activated by the definition of the contact pairs that I presented in the previous slide. For the number of increment, or here you see for the three subcases, for punch in, we have 100 increments, and the convergence criteria are those values for the displacement and the residual load. For the subcase 2, the punch maintained, it is 10 increments, sorry, with convergence criteria more tight. And for punch out, it's 200 increments with just a convergence criteria on the displacement. Again, those convergence criteria are discussed in the nonlinear course. For the maximum number of iterations allowed for each load increment, it is 500. So it means here, for a load increment, I permit 500 increment, maximum number of increment. If the solver is not able to find the solution, the solver will split the load increment, the load increment in two, and will try to find the solution for this split. And the maximum number of bisection, okay, the split, when I say split, the real name is bisection. The maximum number of bisection allowed for each subcase, it is 10. So it is a very aggressive they are very aggressive parameters, but it is due to the fact that the nature of the problem is highly nonlinear. Okay? So it means that it will take a lot of time to reach convergence. So let's have a look at the results to complete this presentation. So let's start with the deformation. The sheet deformation and punch displacement, during the forming and the spring-back subcases are shown here on this animation. We can see how the sheet deforms during the forming subcase as the punch pushes on the sheet until it enters into contact with the bottom of the die. When the punch goes up again, spring back of the sheet occurs, but it does not return to its original position owing to plastic effect. Let's see on the animation. You see the die, the punch go up, but the sheet does not retain the original position. The tangential force here, due to the friction, result in a stretching of the sheet, which in turn induces contact between the punch and the sheet during the complete forming history. During the unloading, the punch and the sheet move simultaneously in an upward direction by remaining in contact. Look again. You see it goes up, it remains in contact, okay? And after that, the punch continue traveling up while the sheet remain in this position. Then the sheet stops moving while the punch continues to move upward to return to its original position. This release of the sheet from the punch allows the sheet to spring back to its final position. So this is really a nonlinear behavior. You cannot capture that with a linear analysis. Now let's talk about the angle after release. So we can calculate this angle at the end of the last subcase when the punch has returned to its original position. The simulation gives an angle of 56.1 degrees. The experimentation data from Alcoa, published into the paper, the minimum and maximum experimental values, because they did the experiment many times. So the minimum and maximum experimental values are between 53.4 and 55.8 degree, okay, which is an error between 0.5% and 5.1%. This represents a strong correlation. Okay, we are in the plus minus 10% correlation. So we can claim a very good correlation for this angle. This curve here shows the load displacement curve of the punch. It is obtained by extracting the data from the 310 load increment of the load history. Again, the correlation with the experimental data is very good. You see here the orange point here are the experimental data, okay, and the yellow curve the simulation. So you see the simulation in the plus minus 10% range, okay, at the end of the forming. So here are few modeling tips that I want to share with you. One of the complicating characteristics in this problem is a very local contact between the plate and the curved shoulders of the die. In fact, the contact is almost a line with a large amount of sliding. So if large elements are used near the shoulder of the die, in the discrete steps of the displacement history, nodes can be identified where no contact is detected. So the following are some guidelines and tips for modeling this problem. First, a fine mesh has been used to describe the contact of the nodes of the plate with the die properly. The surface of the rigid body of the die must be very accurate in order to capture properly its geometry. So it means that when you create your surfaces, the geometry of the problem, it is very important to create very accurate geometry with your pre-processing software. Again, it is what I did, so if you need it, I can share with you the geometric file. The unloading behavior is characterized by the removal of the tool and at the same time adding boundary condition preventing the possibility of rigid body motion. So it is the stabilization that we did with the 1D spring elements. Finally, the unloading behavior should preferably be done in many steps. In our case, it's 200. Note that in these steps, low value of the normal and consequently the friction forces are present, which makes it difficult to obtain a converged solution. So again, we guarantee that by using a lot of steps. So that's it for the presentation of this workshop. You can, on your end, replicate it using all the parameters, all the assumptions I presented you here today. And again, do not hesitate to go through practical finite element analysis for mechanical engineers. This book is available in the FEA Academy website. You can order it online. All the different assumptions, the basic nonlinear assumptions are presented in the book, and so you can dig in detail. Also, you can go through the courses, the FEA Academy courses, which are online on-demand courses, and all the parameters, the modeling techniques and assumptions are presented in detail with many examples again, and all the details of the assumptions. And it is online. Thank you very much for watching. I am Dominique Madier from FEA Academy. See you in another episode of FEA Insight.